Hello everyone, this is Balu. Welcome to my channel Civil Cave. In this video, I am going to discuss about CODAL provisions regarding the design of stiffeners. Before getting into this video, if you have not yet subscribed my channel, please subscribe my channel and also share with your friends who are pursuing civil engineering degree or who are working in the civil engineering industry. Now coming to the first CODAL provision, that is buckling resistance of stiffeners. It is very important to check the stiffener for the buckling at concentrated loads, because at high concentrated loads, it may be at the supports or it may be in between the span. At concentrated loads, these stiffeners are prone for buckling. So it is very important to check those stiffeners for the buckling. So if you consider the practical scenarios here, if you observe clearly, here you can see two plate girders placed side by side and there is a railway track on it, and this is a train which is moving on the plate girders. So if you consider this train as a moving load on this whatever the plate girder, for the maximum shear or bending case, based on the influence line diagrams, you have to find the worst case and you have to find out the maximum bending moment and shear force, and for those forces you have to design this plate girder. And also another one of the important practical consideration is, for example, if you consider a launching girder, there is a gantry moving on that launching girder. You consider that gantry as a series of loads. For example, a series of loads which are moving on this plate girder, and for those series of loads also you have to find out the maximum forces which is going to be transferred to this plate girder. These are some of the practical cases in which you can observe the series of loads which are moving on the plate girder. So for those series of moving loads, based on the influence line diagrams, you can find the maximum forces in it. So it is very important to check the stiffener for the buckling at the concentrated loads. Let us read this whatever the buckling resistance of stiffeners CODAL provision. The buckling resistance should be based on the design compressive stress. So the basic funda regarding the buckling resistance of stiffeners is, you have to find the design compressive stress, that is FCD, and also you have to multiply it with the area of the cross section. So based on that you can get the compressive resistance of the particular cross section. So here also same case, here we are going to consider the curve C because it is of the rectangular shape. So for that rectangular shape, in the whatever the table in the IS 800, it is specified as curve C, and also the radius of gyration being taken about the axis parallel to the web. So if you look from the top view regarding this plate girder, you can observe this cross section. So this is the web running, and also these are the stiffeners which are placed beside the web, and this is the axis which is parallel to the web. They are specifying regarding the axis parallel to the web. This is nothing but the axis parallel to the web, which I have shown clearly from the top view of the plate girder. Now the effective section is the full area or core area of the stiffener together with an effective length of web on each side of the center line of the stiffener limited to 20 times the web thickness. So the main thing is, whenever you are going to check the stiffener for buckling, you have to consider the cross section of the particular area which is going to resist that concentrated load. So the code is specifying that the effective cross section which is going to resist the buckling is the entire area of the stiffener. So whatever the stiffener which is provided beside the web, that entire area you have to consider. But apart from that stiffener area, you have to consider the effective length of the web in which the cross section area is present, that is 40 times the thickness of the web. So if you consider this as a center line of the stiffener, from this center line 20 times the thickness of the web and also 20 times the thickness of the web from the center line of the stiffener. So this is the effective length of the web which is going to participate in the resistance of the buckling along with the stiffener. So 40 times the thickness of the web is also going to help in the buckling of the stiffener. So now what is the effective cross section you are going to consider is, I am going to show with the highlighter here you can see. So this is the stiffener area which is going to help in the buckling of the stiffener, and also along with the stiffener area, this is the area which is of length 40 times the thickness of the web, in which the web you are going to consider, and this cross section is also going to help in the buckling of the stiffener. So this total entire cross sectional area you have to consider whenever you are going to check for the buckling of the stiffener at a particular location. Now the design strength used should be the minimum value obtained for buckling about the web or the stiffener. So I have shown the axis with respect to the web, and also if you consider the axis parallel to the stiffener, you are going to get another whatever the radius of gyration value. So minimum radius of gyration value you have to consider for the design for the buckling in case of this particular cross section in which you are going to consider. Next, coming to the effective length for intermediate transfer stiffeners used in calculating the buckling resistance should be taken as 0.7 times the length of the stiffener. So whenever you are going to check for the buckling, it is very important to find the whatever the effective length. It is based on the boundary conditions of the member. So here the stiffener, based on the boundary conditions, you can consider this as 0.7 times the length of the stiffener. The length is nothing but this is, for example, this is the length of the stiffener. So you have to consider 0.7 times the length of the stiffener in case of buckling check. Now coming to the other provision. So this is regarding the load carrying web stiffeners. So the effective length for load carrying web stiffeners used in calculating the buckling resistance FXD assumes that the flange through which the load or reaction is applied is effectively restrained against lateral movements relative to the other flange and should be taken as. So whatever here they are given is the effective length for the load carrying web stiffener. So this web stiffener, they are assumed that the flange is restrained with respect to the relative moment of the other flange. So that is what they are explaining, that is the top flange in which the load is going to be applied, it is effectively restrained with respect to the relative moment of the bottom flange. So for that whatever the web stiffener, the effective length you have to consider is 0.7 times the length, in which I already given in the previous case, but also in which they have mentioned that the flange is restrained against the rotation in the plane of the stiffener. I already explained regarding the laterally supported and laterally unsupported beam. So the top flange, whenever you are going to restrict, and also that lateral movement is restricted, at that time it is called as laterally supported beam. If the flange is restrained against the rotation in the plane, at that time you have to consider this 0.7 times the length of the stiffener. And also if it is not restrained at all, at that time you have to consider the total length as the effective length for the buckling design. So from this CODAL provision, so for buckling check of the stiffener, the effective cross section you are going to consider is this whatever the effective web area, that is of length 40 times the thickness of the web, and also the total resisting area of the stiffener you are going to consider. So this is the important thing which is specified in this buckling resistance of stiffener CODAL provision. And also the whatever the effective length you are going to consider is 0.7 times the length of the stiffener in case of the flange is restrained against the rotation, and if it is not restrained you have to consider the total length of the stiffener. So this is the important points regarding this buckling resistance of stiffener. Next, coming to the other provision, and this provision is regarding the intermediate transfer stiffener. I already explained about the intermediate transfer stiffener in my previous videos also. If you have not yet watched those videos also, please watch those videos. You will be came to know what is intermediate transfer stiffener in the previous videos. Now coming to this CODAL provision, the minimum stiffeners. So transverse web stiffeners not subject to external loads or moments should have a second moment of area IS about the center line of the web if stiffeners are on both sides of the web and about the face of the web if single stiffener on only one side of the web is used such that. So For example, this is a web and this is a stiffener which is provided about the face of the web, and this cross sectional area of this stiffener, it should satisfy the minimum moment of area condition. So here you can observe that is, that is the minimum moment of area, that is the minimum second moment of area, that is nothing but the moment of inertia, and it should be minimum such that based on the C by D ratio, this is the minimum moment of inertia should be satisfied by the this corresponding stiffeners, that is the transverse stiffeners which is provided about the face of the web. It may be single stiffener or it may be double stiffener, and based on the providing of this particular transverse stiffeners, it should satisfy the minimum moment of inertia condition. So here you can see that is C by D ratio, that is if it is greater than or equal to root 2, C is nothing but the stiffener spacing, and coming to the D, D is the depth of the web, and IS is a minimum moment of inertia, or you can say second moment of area, and it should be greater than or equal to 0.75 times the depth of the web into thickness of the web whole cube. And similarly, based on the C by D less than root 12 condition, and this condition has to be satisfied. So whenever the transverse web stiffeners are not going to take any external loads or any external movements, at that conditions it should satisfy the minimum moment of inertia condition. So this is one of the important CODAL provision regarding the intermediate transverse stiffener. Next, coming to the other CODAL provision regarding the intermediate transverse stiffener is here the buckling check on intermediate transverse web stiffeners. So the stiffeners not subject to external loads or movements should be checked for a stiffener force. So whatever the stiffener, whether it is not subjected to the external loads or movements, at that time also you have to check for the minimum external force, so that it has the capacity to resist that minimum external force, that is nothing but, that is Fq is equal to V minus VCR by gamma MO. V is the factored shear force adjacent to the stiffener. So if you consider a plate girder, this is a stiffener which is adjacent to the stiffener, there may be a certain whatever the shear force, that factored shear force you have to consider in this case. And also coming to the VCR, this is the shear buckling resistance of the web panel designed without using tension field action. I already explained about this VCR in my previous videos, please go through it. So this is nothing but the shear buckling resistance of the web panel. And coming to the whatever the FQD, this is the design resistance of the intermediate stiffener. This is nothing but the buckling resistance of the intermediate transverse web stiffener, which I have discussed in the first slide of this video. So for this particular minimum force, this whatever the intermediate transverse web stiffener should be like designed whenever it is not subjected to the external loads or moments. So whatever the design compressive stress and also the area you have to consider, and for that you are going to get the buckling capacity of that stiffener. That buckling capacity should be greater than the whatever the minimum this force which you are going to find out through this formula. Next, coming to the other CODAL provision, here it is given that stiffeners subject to external loads and moments should meet the conditions for load carrying web stiffeners. In addition, they should satisfy the following interaction expression. Like for the load carrying stiffener that may be subjected to the external loads and also movements should satisfy this corresponding interaction expression. So you all came across the steel design. Whenever the member is subjected to the combination of loads, that may be with the axial force along with the moments, there must be a interaction check you have to consider. Similarly, your stiffener case also, you have to do this interaction expression check. So here for this load carrying stiffener, this is the interaction check. Here you can see that is Fq minus Fx by Fqd plus Fx by Fxd plus Mq by Myq should be less than or equal to 1. Let us go through this whatever the terms. Here if Fq is less than Fx, then Fq minus Fx should be taken as 0. So the difference has to be taken as 0 if it is satisfying this case. Now what is this Fq is? This is the stiffener force given above. I already discussed this FQ in the previous slide only. Now coming to the FQD, that is the design resistance of an intermediate web stiffener corresponding to the buckling about axis parallel to the web. In the initial slide only I explained regarding this whatever the FQD. So this is regarding the intermediate web stiffener buckling strength. Now coming to the FX, it is the external load or reaction at the stiffener. So whatever the stiffener you are going to check for this interaction, that particular stiffener at that location, what is the external load or reaction developed, that is nothing but the Fx. Next coming to the Fxd, and this is the design resistance of a load carrying stiffener corresponding to buckling about axis parallel to the web. And this is the corresponding design resistance of the particular stiffener which you have considered. And coming to the FQD, this is the intermediate web stiffener, whatever the buckling capacity. Now coming to the MQ, this is the moment on the stiffener due to eccentrically applied load or transverse load if any. At that particular stiffener location, the moment which is developed, that is nothing but the MQ. And coming to the MYQ, this is the yield moment capacity of the stiffener based on its elastic modulus about its centroidal axis parallel to the web. And this is MYQ is nothing but the moment capacity of the particular stiffener which is based on the elastic modulus. So these are the different terms, and whenever the stiffener is going to resist the external loads and also the movements, at those situations we have to definitely check this interaction check, which is very important, whether it is able to resist the external force which is coming onto this stiffener. Next coming to the other codal provision, this is regarding connection of intermediate stiffeners to web. Intermediate transverse stiffeners not subjected to external loading should be connected to the web so as to withstand a shear between each component of the stiffener and the web of not less than this value. That is, shear is equal to thickness of web square by 5 times the width of the support, that is nothing but the outstand width of the stiffener, BS. BS is nothing but the outstand width of the stiffener. And also coming to the TW, this is nothing but the web thickness. So what they are specifying is, if this is a plate girder and this is the stiffeners and corresponding weld which is in between the flange and also the stiffener, it should withstand the minimum shear of this corresponding value, and it is in kilonewton per mm. So corresponding connection should withstand this corresponding shear which is coming onto this connection, and this is the case for which that transverse stiffeners is not subjected to the external loading. So whenever the transverse stiffeners is not subjected to any external loading, at that time that connection should withstand the minimum shear value that is specified as here. And also for stiffeners subjected to external loading, the shear between the web and the stiffener due to such loading has to be added to the above value. So for example, if the stiffener is subjected to the external loading, at that time this minimum shear value plus whatever the shear which is acting on that stiffener, the summation of this force has to be resisted by the connection, and it should withstand that total cumulative value, and also it should have that capacity. So that is nothing but this whatever this provision here. Next coming to the other last thing, that is stiffeners not subjected to external loads or moments may terminate clear of the tension flange, and in such a situation the distance cut short from the line of the weld should not be more than 4 times the thickness of the web. So for example, this is a compression flange and this is a tension flange, and this is the stiffener which you have provided. So whenever this stiffener is not subjected to external loads or moments, at those situations you can leave the gap in between the stiffener and also the tension flange. For example, this is the gap you have provided. So this gap you can provide at a max to max of 4 times the thickness of the web. Whenever this stiffener is not subjected to external loads or moments, you can have the facility to provide a gap in between the stiffener and also the tension flange of not more than 4 times the thickness of the web. So this is regarding the CODAL provisions regarding the design of stiffeners, and this is a part 1 of the video. I have discussed the 5 important CODAL provisions regarding the design of stiffeners, and also there is a other 5 CODAL provisions left. I will discuss in the upcoming videos. So, and also if you like my videos, please like the video, and also if you like my content, please subscribe my channel and also share with your friends. Thank you for watching. Thank you.